How often, as an office worker or teacher, have you thrown away a stack of paper? Despite the success of technologies like e-ink for paperless books and our desire to make our nation waste-free, paper waste still makes up 1/3 of Canada's waste in landfills. Commercial recycling only reuses 68% of the paper that you put in the bin. What if you could recover 100% of that paper and do it right in your office? We at InkSaber are making that as easy as putting the paper in a tray and flicking a switch. InkSaber is comprised of 3 final-year engineering physics students at McMaster University. We are Erol Bowman, Simi, Jayeoba, and Fraser, McCauley, and have taken this project on as a way to culminate our engineering physics knowledge and address the issue of climate change. In 2020, paper mills in the United States produced an average of 942 kilograms of CO2 per ton of paper. In addition, deforestation is another result of the high use of paper. Between 2010 and 2015, tropical rainforests saw a net annual reduction of 3.3 million hectares. Commercial recycling is often cited as a solution to these environmental impacts, but it requires large amounts of energy, typically from oil and coal.
Imagine if every office building had a device, similar in size to a commercial laser printer, that was capable of erasing toner from sheets of paper at the push of a button. This would enable one-to-one conversion of waste paper to fresh blank paper, capable of being printed on again. Gone is the need for shredding, frequent paper recycling, and expensive purchases of large quantities of paper. At InkSaber, we're working towards a technology that can do just that.
InkSaber was developed based on a scientific paper published in the Journal of Cleaner Production in 2019. The paper demonstrated the feasibility of using a xenon flash lamp to rapidly heat toner on coated printing paper well past its glass transition temperature to approximately 160 degrees Celsius. At this temperature, the toner behaves as a viscous liquid, sitting on the surface of the paper. The glossy or semi-gloss coating on the paper stops the toner from being absorbed into the fibers of the paper and makes it possible to loosen the bonds of the liquefied toner to the paper using isopropyl alcohol, without having the paper absorb the alcohol. At this point, it is easy to wipe the toner right off the paper using a cotton wipe or some sort of other liquid absorbing material. The goal of this project is to automate the toner removal process for rapid paper recycling.
Our initial proof of concept consisted of the fuser assembly from a laser printer. A motor drive system was mounted to pull the paper through the device, and PID temperature control was implemented to heat the paper well above the glass transition temperature. After heating, we were able to successfully remove some toner from the coated paper using an alcohol-soaked cloth. There were 2 major issues with this. First, the paper did not maintain its high temperature long after the heating process. Second, the wiping process was entirely manual.
The current prototype that is in the process of being built relies on several lessons learned from analyzing how laser printers work. Heating toner on paper with a xenon flash lamp is expensive and has large power requirements, so the heating process is completed using a set of hot rollers that pinch the paper as it passes through the system. After the hot rollers, the paper is passed onto a heated plate that raises the temperature further and maintains the high temperature as isopropyl alcohol is pumped onto the paper. A wiping mechanism is then lowered onto the paper and vigorously wipes the toner off the coated paper using a lamb's wool pad.
While we have made a lot of progress on integrating the systems and getting them to work together, several steps need to be taken before our device will be fully functional for its intended purpose. First, a new hot plate is being built that will enable better temperature stability. Secondly, the device needs a housing to shield the high-temperature components and potential pinch points. Finally, all parameters related to the physical process need to be optimized to allow for maximum toner removal on a single pass.